Yeah, work through the entire thing together. That would have been all kinds of fun. So let's talk through these. If I go through anything too fast, by all means, stop me and ask a question. Okay? So first of all, key word here, negative charge. Negative charge. If free tries to move from where to where, we know that potentials are based on what a positive charge would do. So we consider a positive charge wants to go from places of high potential to low potential naturally. They feel a force that way. Negative charges want to go the opposite direction. They do opposite of what a negative charge or what a positive charge would do. So in other words, a negative charge wants to go from low potential to high potential. Yes?
Yet despite the charge of its potential energy, it would have just been...
Even if it was potential energy, it would be from low to high, just simply because of the way we define everything based on a positive charge. Okay? Yes?
What about a positive charge? Would it still go from low potential to high?
If it was a positive charge, it would go from high to low. So this is the answer for a positive charge. All right? Anybody else? We did number one. Congratulations. Number two makes you do a little bit of calculus. So given this potential function, it asks us to find the y component of the electric field, meaning it wants us to do this. Ey, or E sub y, is equal to the negative partial derivative with respect to y of that potential function. So we're going to plug in the function that they gave us, so minus del y of xy minus 3z to the minus 2. Did I write something down wrong? No? No, it's good? Okay, it's happy. When I'm taking a partial derivative, anything that's not a y is considered a constant, meaning this entire term is a constant, and when I take the derivative of a constant, it's just 0, okay? So the only thing I'm doing here is this constant times a y, and I've got a negative out front. So in other words, this is just going to become x, and then the negative, so the answer is C, okay? So the last term is considered a constant, taking the derivative of constant is 0. And then we have a constant times y, so the derivative of that with respect to y is just x, and then there's a negative out front. Okay? Anyone? Anything? I got a question for you. Have you ever had a professor that came in with a stack of graded exams, angry about it? Yeah, and brought them in and was slammed them down or threw them at you or anything? I'm just curious if professors do this. I haven't done it. It's happened. And then yelled for a while. Yeah. What do they say? Wow. Yeah. Mad for not understanding, and then tell you you're incompetent. Yeah. Seems like you've really taken these words and stored them in the back of your head. These experiences are...
See the one where the professor is in the coffin and he's like, those test results had me dead.
In a coffin?
Yeah, in a coffin.
Wow, that's impressive. There's a lot of commitment to the anger there. You really, wow, impressive. Number 3, an equipotential surface. An equipotential surface. Looking at these options, just think back to those diagrams we had with equipotential lines and electric field lines and the way they interacted with each other. They were always perpendicular. Okay, the electric field is always perpendicular to equipotential lines or surfaces or just equipotentials, however you want to state that. Okay, and if you're a little confused by that still, go back and look at the slide where we had graphs showing both of those together, and you'll see that they're always perpendicular, right? Number 4, a negative charge is moved from point A to point B along an equipotential, meaning as it goes from point A to point B, its potential doesn't change. This is the same idea if I'm talking about gravity as if I take an object and keep it at the exact same height and just move it over. Okay, I haven't moved it up or down. I haven't worked against or with gravity. Notice the word work kind of just slipped into my sentence there, okay? If I'm not changing potential, I'm not doing any work. So, in other words, which one is this? No work is required to move the negative charge from point A to point B. If the potential doesn't change, you don't have to do any work, okay? I like E. E's just enough to mess with you, isn't it? Yeah, that is kind of mean. Number 5, 2 charged objects separated by a distance d. The first charge is larger in magnitude than the second charge. You might remember that the electric force is given by this, K Q1 Q2 over R squared. And that applies to both charges. So one charge is pushing or pulling on the other one with this magnitude, as is the other charge. Both Q1 and Q2 are experiencing the exact same force. The only thing that's different is the direction. If they're pulling toward each other, if they're attractive, well, those forces are in the opposite direction. If they're repelling, they're in the opposite direction, okay? But the magnitudes are equal. So we can say that the answer is C. The charges exert forces that are equal in magnitude, but opposite in direction. That's the first 5. How are we doing? You got them all right? You just got them all right, right? Fantastic. Good job. I'm very proud. See, I'm saying nice things. I'm smiling. Maybe I already got my anger out during the grading process. If you see any blood on your paper, that was just me just being like, you know, that kind of, you know. There shouldn't be any blood on the pages. Number 6, is it possible to have a 0 electric field value between a negative and a positive charge along the line between those 2 charges? So, positive and negative. If I drop a positive charge anywhere in between those 2, we know that it's going to feel a force that direction. It'll be attracted to the negative and repelled by the positive, which means that at all points in between those 2 charges, there will be an electric field pointing toward the negative charge. So, no, a 0 electric field cannot exist between the 2 charges. I'm getting a call. Should I take it?
Yes.
It's from Tennessee.
Yes.
Even better.
I'm kind of thinking it's probably spam, don't you?
Take
Put it on
it.
speaker.
You know what's going to happen. If I push answer, it's going to be like, hello. And as soon as you say the second hello, that's when it kicks in, because the computer needs a second to actually like click over to a human, assuming it is a human. Could just be a bot. Ah, it stopped. You know how many phone calls I get that I just never answered? Even people I know, it's like, oh, cool. Nah, I don't want to talk. Yes.
So if you do that worse in final part 1, do this one, replace the final part 1 too?
Yeah, we should do that. If you do worse on the final, like it replaces everything. No, we're not going to do that. No, I won't penalize you either direction. Whatever's best.
He meant if you do worse on the final, this grade go for that.
That's not part of the deal. No. Sorry. It's not on the syllabus that way. But there was a question over here somewhere. No, you're good? No. Number 7. Number 7 was probably the most difficult to sort of see what's happening among the multiple choice. A long line of charge with charge per unit length, or in other words, charge density, lambda, is on the x-axis, and another one is on the y-axis with their centers crossing at the origin. So let's say we have an x and y axis. This is saying that we have some line of charge density here and another line of charge density there. It didn't give either one of these as negative, so a positive sign is assumed there. So this is positive lambda, and this one is positive lambda. If you wanted to label those 1 and 2, like so. One is on the x-axis, the other is on the y-axis. In what direction is the electric field at point z equals a on the positive z-axis if both of those are positive? Okay, so it did explicitly say it. In other words, the positive z-axis is coming directly out here. So at some point, and apparently the xy plane is moving all over the place, which makes things a little hard, right? At some point out here, which direction is the electric field? Which way would a positive charge be moved? Yeah, it's going to want to get away from all of this, right? So it's going to point that way. Your question?
So could we just look at it like a cylinder that's like projected outwards?
I'm not sure how.
So like if we were to just make a circle around the plus, we know that the field that is being induced by it is covered by that circle. So if we were to put a z coordinate outward, it would be kind of like a tube extending off the page.
Maybe, kind of. Did you get the right answer out of that?
Out of this explanation, yeah.
But not out of that one.
Yeah.
You can show me what you did later if you want. See if I can get from there to an answer.
Okay.
Okay. Yeah. So positive direction. Are we okay with that? Yeah. At some point here, it's going to be pushed away from all of those positives. So all of this is positive. Let's go ahead and label that just so we have it. So let's see. The positive z direction is the direction of the electric field because that's which direction a positive charge would be pushed. If you want to get your exam, there's a stack right here. I'll let you find that real quick. Let's see, number 8. Number 8, the figure to the right shows 3 electric charges, Q1, Q2, and Q3, with the electric field lines. What are the signs of the 3 charges? Keep in mind that the electric field lines point out from a positive charge because it pushes away other positive charges. So you can see that this one on the right and this one on the left are positive. They have the lines going out from it. Notice the electric field lines are pointing in toward Q2 because a positive charge would be drawn to it, which means that it is negative. So our answer is positive, negative, positive, which looks a whole lot like A. Okay? Positive, negative, positive. We're through with 8 of the 10. Any questions before we do number 9? All right. Yes. A rectangular area is rotated in a uniform electric field from the position where the maximum electric flux goes through it to a new place where only half of the flux goes through it. What is the angle? Let's write our equation for electric flux. EA cosine theta. EA cosine theta. So, if we assume that the only thing that's changing is the angle, so it didn't tell us the electric field is changing. In fact, it said it's a uniform electric field. And this area is the same the entire time. It's the area that's rotating. The angle is changing. If it goes from a place where I have maximum flux to half the flux, I need to find out what the angle is. Okay, so we're going to say that this stays the same, this one stays the same, and this is going to become 0.5. Okay, instead of being 1, if it was 1, I would have the maximum amount. If I have 0.5, I've dropped the amount of flux by half. What theta plugged into cosine gives me 0.5? Yeah, you could just punch some numbers into your calculator until you figure it out, or take the inverse cosine of 0.5. To get that, I need theta is 60 degrees. Theta is 60 degrees. I tried to help here just a little bit because there was an answer that was an answer E that like everyone wants to take because you just want it to be like, oh, half, 45 degrees. And everybody jumps to that answer. So I took that out to try to make you think a little bit more. But I'm thinking a lot of you might have been like, I want 45 and it's not there. And then you weren't sure what to do. So life got a little confusing. So who knows? Is everybody okay with that answer? Cosine of 60 gives me half of the flux. And then finally, number 10, we've got 2 charges. One is positive, one is negative. What is the direction of the electric field at point P? So keep in mind that the electric field is tangent to those lines, and it needs to be going from the positive charge to the negative charge, meaning that the electric field vector at that point is tangent and points in the direction of A. Okay? If we wanted to draw the electric field vector at more locations, it kind of looks like that. So it's always tangent and working its way from positive to negative. And you can see that implied a little bit on some of the other lines. Those are the multiple choice. Those are the answers. Does anybody have any questions? Yes.
Can you just explain it again?
Explain this one.
Yeah, the last one.
So the electric field lines point away from positive and toward negative. So that one is the only one that didn't have arrows on it. So we draw the arrows pointing in that direction, and it's tangent at that location on the curve. Anybody else? Does anybody want to throw anything at me? Please don't. Does anybody want to boo? Boo? Some slight boos that are out there. Yeah, you boo me, I'm going to boo back. That's just going to happen. I promise you now. All right, so let's move on to the problems. Our two problems we need to work. Number one is 4 parts of Gauss's law. Parts, it kind of gets progressively more simple as you go through. We start with the hardest part, which is part A. Part B takes a little bit less work. Part C takes no work at all, and I think most of you, if not all of you, got part C. And then part D takes just a little bit more work than part C. So let me step through this and show you how it works. First of all, notice we are given a total amount of charge, and we are told that that charge is everywhere throughout a sphere that's insulating. Remember, when something's insulating, I can take charge and I can distribute it, and it stays there because the electrons aren't free to move around and move the charge around. So in other words, we have something that maybe looks like this. We've got a sphere, so let's just draw a cross section, which would be a circle, and we've got charge that's sort of scattered everywhere in the sphere. And it says that it has a radius r equals 2 centimeters. So this is 2 centimeters. Okay? Part A asks us to find the electric field at a distance r over 2. So halfway out, so at 1 centimeter, I want to find the value of the electric field 1 centimeter from the middle in any direction. All right? So that's where we're going to draw a Gaussian surface. So this has radius r over 2. The trick for this is going to be figuring out how much of that charge is enclosed inside the Gaussian surface. All I know is charge density, or maybe I can calculate a charge density. I don't know how much of my charge, and the answer is not 2, right? 2. I drew 2 inside. That's not the answer. That's supposed to be funny. Laugh. Or boo. Yeah, wow. Now you're just doing whatever I tell you to do. Laugh. Ha ha. Boo. Boo. Cluck like a chicken. Yeah, see, you can't, yeah, you're like, I don't know. Jump on one leg. Like, I don't know what we're playing now. Stop. It would have freaked everybody out if the force had been in play. It's like, stop. And it goes, pins itself to the wall. I'll save that for later in the semester after you're a little more scared of me. Yeah. So let's see. Gauss's law, E dot dA equals Q enclosed over epsilon naught. The left side of this applies to the Gaussian surface. So the electric field is going to be a constant value at that distance, which leaves me with the closed surface integral of all these little bits of surface area. And we're talking about the surface area of a spherical Gaussian surface, which means that's going to be 4 times pi times r squared, but my r here is r over 2. Okay, it's specifically the spherical surface area of this red dotted line. So we'll say surface area of spherical Gaussian surface. That's the left side. That side's done. Okay. On the right side, I can't just write down Q enclosed is 18 microcoulombs because some of it is outside where I drew the Gaussian surface. I need to figure out how much of it is inside here, all right? So what we can do is a couple of different things. First of all, the volume charge density is all of the charge divided by all of the volume or any part of it, okay? So it could be Q, which is 18 microcoulombs, divided by whatever the volume of the green sphere is. That's one option. But I could also just take part of it and say that it's Q enclosed over the volume enclosed, in which case I'm just looking at the part that's inside the red dotted line, okay? Whether I take the whole thing or just this chunk out of the middle, the density should be the same everywhere, okay? It's like cake, right? If the cake has a certain density, it doesn't matter whether I take a piece of cake over to the right side or the left side. All of it, you look at it and you're like, hey, this cake has a certain density of cakiness. I don't know, of cake material. All of it's the same. It doesn't matter which piece or which bite you take, okay? So we can take this and rearrange it so we have something to plug in for Q enclosed. It is the density times the volume that's enclosed. So let's write that down over in our equation. The density times the volume enclosed. And we still have an epsilon naught in the denominator. Let me pause there for a second and see if there's anything you'd like to ask. Anything? You wanted to stop moving, or you want to ask a question? You look like you were reaching out to be like, yeah.
One of the problems I was just on that is even the point charge, how do you differentiate it so where you know it's a point charge or not?
It will usually say there is a charge or a point charge specifically. Anytime you see something about distribution, something that's scattered and spread out in a lot of different places instead of in one location. Okay. Anyone else? Let's keep going and see where this gets us. So, continuing on the right side of this density thing I don't really know anything about. The volume enclosed is the volume of this red sphere that we've drawn. So that's going to be a spherical volume. It's 4/3 pi r over 2 cubed. That's the density, or excuse me, the volume of the red dotted line. So where does that get us? All of a sudden I'm seeing a lot of r's, pi, a couple of 4's. I think we can kind of simplify this a little bit before we move on. So let's see, the pi's are going to cancel out. The 4's are going to cancel out. And let me just rewrite what I have here. So now I've got e times r squared over 4 is all that I have on the left side. And on the right side, I have the density, I have an r cubed, and then in the denominator, I have a 3 times an 8, so that's 24. 3 times 2 cubed. So let's solve that for E. Solving that for E, we've got density times r cubed times 4 over 24r squared. Stop hitting me, screen. Yes. Did I make a mistake? Did I leave it? Did I make it go away? Yes, I did. I goofed. I always forget the epsilon. There it goes. So it's there, and it's also here, which means it's there. So it's in the denominator everywhere. Thank you. So let's see, I've got an r cubed and an r squared, so 2 of those are going to cancel. And I also have 4 over 24, so that's going to simplify a little bit as well. So this becomes, let's see, density times r over 6 epsilon naught. Would everyone agree with that, perhaps? Maybe? It's all simplified down to that so far. So here's the problem. I'm looking for the electric field. I know R, that's not a problem. And I know epsilon naught. I don't have this density. If I could calculate the density, then everything would be okay. Look back up here at the top. I've got the information I need to calculate the overall density. I have the total amount of charge, and I know the size of the whole sphere. So that's something that I can calculate separately. So let's go over and do that. And I'm going to need your help getting this number. I didn't do this intermediate step. Instead, I plugged it in, but I think you might like to see it this way better. So let's say this is Q total over the volume total. And this is for the insulating sphere. That's not how you spell sphere. Let's try that again. For the whole thing, we have these numbers. We can solve for a value for the density and plug it into our equation, and then we'll be where we want to be, okay? So let's see. This Q total, we know what that is. The total volume is 4/3 pi r cubed, where r is the actual 2 centimeters there at the top. So this is 18 times 10 to the minus 6 over 4/3 pi 0.02 cubed. Somebody punch that in your calculator and let me know what you get. I don't know why I always say punch it in your calculator. Somewhere I picked that up. I had a professor in college, he always used to say mash. He'd talk about mash the buttons. I don't know why he said mash. Mash the buttons on your calculator. Tell me what you get. Who knows? What do you say? What do people 20 years younger than me say about entering numbers into their calculator?
Plug it in.
Plug it in to the calculator? Maybe that's just you. You're the only one who said that. Is anybody else? Is there some hip lingo that I'm missing out on for calculator punching? No? You're like, just shut up, Dr. Longhorn, and keep working. You're an idiot. You're old. I know. What'd you get? 0.537? I'm going to trust that that's right, because we're going to plug it in over here with the other values that we have and hopefully get the number that I have. So 0.537 times 0.02 divided by 6 times 8.85 times 10 to the minus 12. And yes, this part A is probably, no, definitely the hardest part of the entire exam. When you have the number, tell me, and then I'll tell you if you're right or wrong. Don't everybody tell me at once. I thought I heard someone say 2. I like 2. There's a 2 in it. I would agree with that. What'd you get? 8th or 6th? Which one? 2.02 to 10 to the 8th. I do have that. Good. And what are the units for electric field? Newtons per coulomb. Good. That is our answer for part A. Ugh, that was a lot of work. That was the part of the test where it's like, okay, I actually need to test you. So if, like, for whatever reason the other things come easy to you, which maybe they did, maybe they didn't, I need to find out if you can do something slightly harder. Any questions in there anywhere? Study this. Examine this. Make sure that if I were to give you this exact same problem with a little twist, because I wouldn't give you the exact same problem, that you could apply these concepts to something that was similar but a little different, okay? Let's do part B. Part B, calculate the magnitude of the electric field a distance of 2r from the center of the sphere. 2r is outside the sphere. 2r is outside the sphere. So if I go back and draw a new Gaussian surface, 2r, well, I don't really have room, but you can imagine it would be like way out here somewhere. Okay, a distance of 2r away from the middle. Well, now if I ask the question, how much charge is enclosed by the pink line? All of it, right? Every bit of the charge on the sphere lives inside that, which means I can sort of go back into the problem here where I had to insert Q enclosed and actually use all of the charge. So I'm going to have the exact same thing on the left-hand side, well, except for this r over 2 is becoming 2r. We're going to follow the same approach. And over here, I don't have to do all of this density stuff. I can just put in 18 times 10 to the minus 6 and divide by epsilon naught. So let's do exactly that. Starting with Gauss's law, E dot dA equals Q enclosed over epsilon naught. This is again going to be E times 4 pi, and this time it's 2r squared equals Q enclosed over epsilon naught. And we're just going to clean up what's on the left, solve for E, and plug the numbers in. This one happens fast. Anytime you have all of the charge enclosed, life gets relatively simple. It'll follow an approach like this and not a whole lot more. So let's see, we've got E times 4 pi, and then another 4, and then r squared equals Q enclosed over epsilon naught. So that's E times 16 pi r squared. Yes, I'm getting tired of rewriting the right-hand side of that equation, but I'm trying to be somewhat complete. So E is equal to Q enclosed over 16 pi epsilon naught r squared. So how much Q was there? 18 microcoulombs. And I've got 16 pi. Epsilon naught is 8.85 times 10 to the minus 12. And r is just r, which is 0.02. It's the radius of the thing at the beginning. And then somebody's going to tell me what all that gives you. Yeah. Interestingly enough, that's exactly half of what we had before. We had a 10 to the 8, 2.02. Now we've got 1.01. 1.01 times 10 to the 8, not minus 8, 8 newtons per coulomb. Thank you. And that's the end of part B. Yes?
So you say interesting, is it really coincidental or
First of all, I didn't intend for that to happen. There's a reason, but I'm having trouble seeing it. Because anytime something like that happens, it's usually not coincidence. There's sort of an interpretation.
because ultimately there's no difference other than the radius, and the radius is a change factor too.
The radius is what?
The only difference between the two levels is the radius, because the charge density will be the same ratio as the charge enclosed.
True. But of course, doubling the radius quadruples the surface. But we also
Half it, quarter,
yeah, it's ratios
yeah.
that are hiding in there.
So effectively,
But it's not terribly important. Yeah.
so even if you got it right, but you use the wrong formula, you still get most of the points wrong.
If I didn't see Gauss's law and then these following steps to get to that number, then yeah. Especially if you came at it like this, which gives you the exact same answer, but that's not how you can solve this problem because that is only for a point charge, and this is not a point charge. If that gives you the answer, which it does, it's just so this can't be used here. I'm sorry. I know, it kind of hurts. Anybody else? Yeah. If you were able to make some justification for using the equation, like you wrote some things down, and I saw this maybe on one or two papers where it was like, from Gauss's law, this is true, and then I have this equation. Like, in other words, you're kind of using what you had in part A to jump down to that. I tried to give credit for that. But if you think there's something there that deserves credit, I'll always look at anybody's paper a second time if you need me to look at something. Okay? Part C. Part C. Okay, part D. Yeah, really. I just wanted you to see that if it's conducting, the electric field inside of a conducting material is always 0, and R over 2 puts me inside the conducting material. So you're supposed to know that the electric field is a conductor. So there are 9 points, okay? I did expect you to write something there saying that, like, it's in a conductor, and that was the explanation. As long as I saw, like, 6 words, like, that was enough of an explanation, and I was happy with that, okay? Part 9 should be the exact same answer as Part B. And I actually didn't necessarily need to see any work there at all. If you made a statement saying same answer as Part B, which is 1.01 times 10 to the 8th newtons per coulomb, I was happy. The reason for this is that, yes, if it's a conductor, the charge is going to distribute differently. So now I'm going to have a sphere, and my 18 microcoulombs is all going to be here. But if I do that, and then I'm looking for the electric field out here, well, the same exact equation applies. Like, Q enclosed is still going to be all of the charge, which means you could do all the work in Part B again. You're just going to get the exact same answer because Q enclosed is the same value, okay? And you're at the same distance. So C and D was meant to try to give you a little bit of a break after A and B. I don't know that it worked, but I tried. And you're thinking, like, we don't care if you tried. I still didn't get it right. I'm sorry, but you'll learn eventually. It'll be fine. It'll be great. Let's do the other problem, unless there's questions here. Anybody? Gauss's law stuff? How do you feel about Gauss's law? You're allowed to boo if you need to. Just get your anger out about Gauss's law now. Direct it at Gauss's law, not at me. I'm not Gauss. If I was Gauss, I could understand if you were angry with me, but I'm not. I didn't have anything to do with it. It's well before my time. All right, let's do the other problem. Number 2. Number 2, consider a square, which is 1 meter on each side, and we have some charges placed at the corners of the square. So let's draw the situation. We have a square. Look at that terrible square. Thank you for being, that's more of a rectangle than a square, but it'll get the job done. Let's see. So I'm just going to assume that this corner sits at 0, 0. You could kind of situate it anywhere. It would be fine. So here we have things are falling apart over here, apparently. I kind of feel like the screen is angry at me. Like, it's really got an attitude today. I don't know what the deal is. So let's see. I'm going to give these charges some names. You didn't necessarily have to do this, but just to help me keep track of things. So I'm going to say that this one is Q1, and I'm going to put a positive there to help me remember that it's a positive 4 microcoulomb charge. I'm going to call this one up here Q2, which is at 1, 1. And then we've got Q3 down here, and that puts Q4 up there. And let's see, Q1, 2, and 3 are all positive, and Q4 is negative. So there's the setup. As exciting as it is, it's a square. Thrilling. Should have had like a trapezoid or something, just to mess with you. No, no trapezoids. No. Parallelogram? A rhombus? Anybody remember all these names for shapes? I don't know. It seems ridiculous. Rhombus. I like a rhombus. What is a rhombus? I don't remember. It's related to a square in some way, though.
It's a square version of a parallelogram.
It's a square version of a parallelogram, so if I just like tilt these 2 lines, that's a rhombus.
No, that's parallel.
Well, a rhombus is a subset of a parallelogram. Okay, we don't need to know any of this, but all of a sudden now some of you are like, you're speaking my language. Let's do that instead of this stuff. Okay, maybe on the final exam we should have a rhombus. That'd be fantastic. I'll just write rhombus and you have to figure out what it is. Yeah, that'll make everybody happy. No, let's get rid of that. Rhombus is gone. So find the magnitude and the direction of the electric field at the center of the square. So we're going to the middle of the square and we're going to try to find something about the direction of the electric field. First thing, I'd kind of like to know how far away I am from those charges. That's going to come in handy because I need to know R. It's going to be the same for all 4 of them, So I'd like to know this distance. This is distance r. Let me make that a dotted line just because we're going to be drawing in some vectors in a second. I don't want to confuse it. So this is distance r. It is the same in all four directions. So let's just write it in one direction and do the math. So this horizontal line I just drew, how long is it? 0.5. It's half a meter, right? So this is 0.5. This vertical line, how long is it? It's 0.5. So r can be found using the Pythagorean theorem, and we could say that r is the square root of 0.5 squared plus 0.5 squared, which is 0.707, I think is what it was. Yeah, meters. Okay, that's the first step. This point in the middle is 0.707 meters from all four of the corners of the square. Okay. Next thing I'd like to do is think a little bit about the direction of the electric field before I do any calculations. So if I drop a positive charge in the middle, how is Q1 going to affect it? It's going to try to push it this way, right? How is Q2 going to affect it? The opposite way. What are the values of Q1 and Q2? They are the same, which means they're going to generate the same electric field at the same distance. So we could draw two vectors here. We could say that maybe this vector is electric field from 2, and this vector is electric field from 1, and they're in the opposite direction, and they are equal. You could do the calculation and see that that's true. So we could say that the magnitude of E1 is equal to the magnitude of E2, and in opposite direction. So they cancel out. You don't necessarily have to recognize that. You could do all of the work to add these in, and they will eventually, somewhere in your math, cancel each other out, and everything is happy. If you do recognize it, though, at this stage, it saves you a good bit of work. So that's intended to give you an opportunity to make the test a little bit shorter. For the other ones, for Q3, how would it affect a positive charge here? It'd push it up this way, right? For Q4, what would it do to a positive charge here? Also that way, okay? So I've got two other vectors, and this is where I'm starting to regret that my square isn't quite a square, because things aren't looking as perpendicular as I'd like them to. But you can imagine there are two vectors pointing up this direction, one from number 4 and one from number 3. If I can find these two magnitudes and just add them, that's going to be the total electric field. Technically, the way you're supposed to do it is find all 4 of these vectors and do the math to do vector addition for all 4 of them. But thankfully, 2 point in the same direction and 2 point in opposite directions, which saves us a lot of vector work, okay? So let's see, E3 is equal to E4, or is E3 equal to E4? Are those equal? They are equal because I have 3 microcoulomb charges. So E3 is equal to E4, and that is equal to K times Q over R squared, where Q is either 3 or 4. Take your pick. Let's make it 3. So this is 9 times 10 to the 9. And Q, 3 or 4, we're just looking at magnitudes here. So that's 3 times 10 to the minus 6. And R is 0.707, and we square that. Anybody have that number? $144,000? Could be. I'm not sure. We'll go with that for now. So if I want the total at that point, it's going to be E3 plus E4, which is really just 2 times what I just got.
Sorry, that's wrong. I used 4 instead of 3.
Used 4 instead of 3?
Yeah.
Should be the same thing.
No, as I've been showing, 4 microcoulombs.
4 microcoulombs. Okay, so what is it with 3 microcoulombs?
54,000? Do we have confirmation of 54,000? But then 54,000 for both of these and hoping for the best. Looks reasonably close to the number I ended up getting. So somewhere right around like 1.1 times 10 to the 5th newtons per coulomb. I've got 1.01 times 10 to the 5th, so something might be a little off somewhere, but it's close enough. 1 times 10 to the 5th. Let me stop for questions. Who's got some? Anybody? No? Seems to be getting darker the longer this class goes on. Would you agree? Like at lunchtime, it was all sunny, and then I passed back the test and the clouds rolled in. And now we talk about the solutions. I feel like thunder and lightning is about to happen. Just, you know, the evil is upon us. So that's part A. Let's do B and C, and then we'll be done with this exam. Part B, find the electric potential at the square center. The key here is that this is a scalar. So if I want to find the total electric potential, it's V1 plus V2 plus V3 plus V4. I have one term for each of them. So that's going to be KQ1 over R. R is the same in all cases, plus KQ2 over R, plus KQ3 over R, plus KQ4 over R. That was ridiculous to write all that out because it's really just K over R times Q1 plus Q2 plus Q3 plus Q4. Yes?
For part A, what was the direction?
Oh, what's the direction? The direction is, well, these two cancel, so what's left is just that. I was pretty lenient with that. If you calculated an angle, great. If you just said toward the charge on the top left, that was good. Just something saying that it's up there, okay? The direction is to the top left. So let's say direction. There we go. So let's see, Q3 and Q4 are the same, but one's positive and one's negative. So these two are gonna cancel each other out. These are the same, but opposite sign. So we really have K over R times Q1 plus Q2. So that's 9 times 10 to the 9th over 0.707. And Q1 plus Q2, I think both of those were 4. So that's going to be 8 times 10 to the minus 6 coulombs. Which should give you something on the order of 101. I rounded a lot. Just anything in that region was acceptable because people might have come at it different ways. 101,000 to 102,000 volts should be your answer. Somewhere in that region. And then for part C, prepared to hate me. You just get yourself ready. Because I saw how much work many of you did on the last page of the exam. And I didn't want you to do that much work. I really didn't. Maybe I should have even put in a statement. Don't do much work on this, because if you do, it's overkill. You know, overkill is a funny word. Have you ever really thought about that? It's not just kill. It's like you kill a lot. Like you didn't just kill the thing. You killed it and get like, it's terrible. Overkill. What a terrible idea. Anyway. F is equal to QE. F is equal to QE. E is from part A. Q is what we were just given, 3 times 10 to the minus 6. And what was our answer from part A? 1.1 times 10 to the 5th. And that's all you need to do, which is somewhere around 0.3, I think. Give or take a little bit. That's 0.3 newtons toward the top left. points in the same direction as the electric field because it's a positive charge. If it had been a negative charge, it would point in the opposite direction toward the bottom right. So something to be a little careful about. Does anybody have any questions? So your question is there no curve? Huh. So it's just a simple yes or no answer. I am unsure what to do. I need to think about it. At this point, you have your grades. Let me look at everything and the distribution and stuff and kind of just see what makes sense. Because you do have a chance to redeem yourself. So maybe that should be the curve. And we're not done yet. It's 34. Where is everyone going? Don't you want to start the next chapter? Wow. The strongest response of the day. Why is that? Like I give you exams back, you get a grade, no response to that. And it's like, start the next chapter, oh! And then there's like moaning. Okay, we won't start the next chapter after something like that. But Thursday, be prepared. We're going to talk about capacitors. Capacitors are cool. I'll see you then. Bye.
Can I ask you a quick question about number C?
Please do.